Hello and welcome. Today we're going to talk about Fourier series and specifically the conditions for convergence. So recall a Fourier series. We have some function. The goal always for Fourier series is we start with f of x, which is a given function. We have this given function, it could be a variety of types. But the idea is that we want to make, so we also have this thing called the Fourier series of it, which I'm going to call f of n of x, which is equal to a0 plus the sum from n equals 1 to capital N times an cosine n pi over Lx plus bn sine n pi over Lx. All right, so we're going to take this, we'll take our interval that f is defined on, like so, and from previous times we've always gone from 0 to L, but this time it just simplifies our notation if we expand our range to negative L. So we have a symmetric interval about 0. And that doesn't change anything fundamentally about what we do, but it just makes some of our math work out a little bit nicer, a little bit cleaner. All right, so what we want is we want f hat of n to approximate f of x. Right, so we also have this distance function, which we use for our approximation. And this distance function, this is usually called the function norm. And in this case, it's squared. And that's just to simplify our calculations. And it's equal to the inner product, the functional inner product of f n hat minus f with itself. All right, so how do we write that? It goes from negative L to L of fn hat minus f quantity squared dx. All right, so the idea is when these two functions differ from each other, it'll create some non-zero quantity. We square that to make them all positive, and we add up all of the errors. So you can think of this as an error term. And then we square it because we don't care about the sign. We just care that these two functions are different when these two functions are different from each other on the interval. And we add up all of those, which is the integral, right? So if we have a function here, here's f, and then f hat kind of goes like this. And that's f hat of n. And the idea is that everywhere that there is some difference between these two functions, we're going to square that area under the curve, and that will add up to be some non-zero quantity. And we have from the definition of the inner product, if fn minus f is equal to 0, i.e. that they're for everywhere on the interval, then we know that fn hat minus f is equal to 0 as well. Okay, so so that's the idea. This is, and so we learned an important thing, that if we pick, so let's write this down again. So this is our distance function, and that gives us a way to help us approximate f using our Fourier series. So this is our Fourier series. All right, so let's, with this distance function, f n hat minus f, we're going to square it. and that, of course, is this negative L to L of f minus f hat n quantity squared dx. This norm, if we want to minimize this, we want to minimize that. We learned that it is minimum. So this quantity right here is minimum if an is equal to f, the orthogonal projection of f onto cosine n pi over L x divided by the inner product of n pi over Lx with itself. All right, and the same is true, and that's true for n is equal to 0, 1, 2, 3. And for bn, we do the same thing. We just have the sine term there, dot dot, over the inner product of sine with itself. And that's true for n pi over Lx. And that's true for n is equal to 1, 2, 3. So here with our cosine terms, we get n equals 0, but for the sine terms, we start at n equals 1. All right. So basically our best approximation. These produce the best approximation. And then we should say with respect to our distance function, which we write like that. So the idea here is that, yes, we could use some other measure of deviation between f hat and f, and we might get a different result. But for this particular inner product, this orthogonal projection is the best approximation. Okay, and we've proved that before in a different video. So what we want to do now is ask the question, what about this? What if we take limit n going to infinity does this equal 0? Can we get a better and better and better approximation until ultimately the distance between these two functions with respect to this particular distance function, is it 0? We want to ask that question. So clearly, if this is true, then it means that f hat and f are very close to each other and might be actually equal to each other. So we'll leave that as an open question, but we're going to state that theorem today and realize some consequences of that. So before we can do that, we have to talk about, so what is f? That's the question we need to ask. So first of all, the functions f could be a lot of things. So we have to restrict. We have to restrict our class of functions f, right? Basically, f can't be any function. So what kind of function can we be? We're going to consider only what we call piecewise smooth functions. So what do we mean by piecewise smooth functions? So a piecewise smooth function is straightforward to define. It means that so we call this piecewise smooth if if 1, f is continuous except on finitely many points, in the interval negative L to L. Okay, and 2, we need one more condition. F prime is continuous except the same thing on finitely many points. So both are true. Okay, so what do we mean by continuous on finitely, except on finitely many points? So let's draw a picture of an f, just to give an example here. What we have here is, I'll take this particular example. We'll make it concrete here. So this is, it's going to go from negative 3 to 3. We're going to have 0 right there. We're going to have a function that is just a piecewise linear function. Like that. Okay, so there's a function. So we can identify here that the function has a few discontinuous points, right? There's one there, there's one there, and there's one there. So we see that we have discontinuous points at these values there. But there's finitely many. So you know, this condition of piecewise smooth isn't really that restrictive. As long as there's finitely many breaks in this function, we're okay. There's no problem there. I'm going to draw this a little bit crisper though, and notice that there's this point here where we have continuity, but we have a line that's going, it has a positive linear slope, and then it has a negative linear slope, but it's still continuous at that point. So now this is f. Now let's go to f prime. I'll draw that. So again, I'm just going to do an artistic rendering of this. This isn't a quantitative, but rather just, so we see here it has a positive slope, so I'll just say that the positive slope is constant. And here the positive slope is the same, maybe a slightly different, maybe it's slightly higher. But we see here there's a break, and now we go to a negative slope down there. And then we go back to a positive slope. And then we go to a negative slope. Okay, so we see here there's also discontinuous points. But now how many are there? You see that there are 4 discontinuous points rather than 3, but there's still only finitely many, so we're okay. So we conclude that f, this particular value of f, is piecewise smooth. All right, so let's go to some other examples to just firm up this notion of what a piecewise smooth function is. So clearly we can see already this is a fairly broad class of functions. So let's talk about some other functions. But let's now ask the question, you know, what kind of functions are not piecewise smooth? Right, because it seems like that's a pretty crazy case if it has infinitely many discontinuous points on an interval. So I'll just give you a simple example, or a straightforward example, just to give you an example of the type of things that aren't piecewise smooth. So let's talk about f of x, the function that's equal to 0 for x that's rational, and it's equal to x if x is irrational. All right, so that's obviously a very weird function. And let's say we're going to go over the interval, we'll go from negative 3 to 3 again, just like before. So I can draw this function straight and easy enough. So here's f. Here's -3. Here's 3. There's 0 in the middle. And we see, so when x is rational, you can think of this as sort of like every rational number on the line. There's infinitely many points where it's rational. And we have 0 for all of those values. All right, but then for when x is irrational, there's a lot of irrational points also that fill out this line interval, and we can think of it as sort of making a dotted line. Now that's just an artistic rendering, but the idea is that if we're at a rational point, then we're at 0. But then when we move to an irrational point, we immediately jump down to some other value, and then it comes back up. So it's jumping between rational and irrational values infinitely often. And so this is going to have infinitely many discontinuous points. So we say not piecewise smooth. All right, so is there a point actually where this function is continuous? Is it continuous anywhere? Well, it turns out it is continuous at 0, right? Because here, the limit of each of these two functions individually, the limit is 0 in both cases. So it's continuous only at x is equal to 0. So there's only one point where the function is continuous at all. Everywhere else, it's discontinuous. Okay, so that's just an example. So clearly, we can conclude that this is pathological. It's a perfectly well-defined function, but is it going to be any use to we applied mathematicians who want to solve problems in the real world? And in that sense, is it's not a useful function. So the kind of categories of functions that are not piecewise smooth are usually pretty crazy, and they're not things that we really care about anyway. There are some exceptions to that, but in general, it's not really something we need to worry about a whole lot. These aren't really useful ideas. So, piecewise smooth functions. So we conclude that piecewise smooth functions should, cover most functions that are useful. Okay, so so piecewise smooth functions are certainly a very broad class of functions that will serve us well in our any kind of purpose we have. So let's now we need one more definition before we can get started on the theorem, and I'm just going to get another sheet of paper here. Let's talk about another thing, which is okay. We have f. Let's say we draw out a function f, and I'll just put it like here. There's our 0, there's our L, there's our negative L, and it's some function that does, we'll just draw something like that. Okay, so what I want to talk about now is we're going to define another thing. I'll call it f tilde, which is the periodic extension. So what is that? What do I mean a periodic extension? What I mean is we're going to extend the function to the real line. So we're going to go from negative L to L, and it will be I'm gonna change my function just so it's a little easier to draw. I'm just doing some change in my artwork because I don't want the artwork to become a burden. There we go. So this function goes like this. It goes up, it goes down, and it goes over like that. And then when we go to 2L and then 3L, it does the same thing again. And then when we go to 5L, it does the same thing again. And now if we go backwards, there's the same thing again. So what we do is we just do repeated versions of f onto the real line. Notice how when we do so, if the function values are different at either end of the thing, it creates a discontinuity at every point where the intervals join. All right, so again, we call this function here f tilde, and I call it a periodic extension because what happens is that f tilde, now if I have a value at a particular value of x, if I add plus 2l to it, right? The value of f is the same. Right? In fact, we can even write this as f tilde has any value of x plus 2nl. They will always be equal for n is equal to 0, 1, 2, 3, so on and so forth, but also -1, -2, -3, and so on and so forth backwards. Okay? So this is the periodic extension. It literally just takes copies of f and just pastes them onto the real line. Okay, so again, this is just a definition we need to have so we can better talk about Fourier series. So now we're ready to go. We have our definitions. We have our definitions of piecewise smooth. So notice that again, that f tilde, when the function itself doesn't have values at -l and l that are equivalent, there creates discontinuities in the periodic extension. But you know, those don't necessarily those aren't necessarily a problem. But we just have to note that there are these discontinuities there. Okay, so let's talk again about some examples of periodic extension. So for instance, I'm going to talk about f of x is equal to sine, sorry, we'll go with sine pi x, and we're going to take it over the interval. We'll go from 1 to -1 to 1. Okay, so I'll draw out this function. There's 0. We're going to 1 and -1. So what does this function look like? It's going to go like this. So of course that's just going to create a sine wave like so. And so on and so forth. But now let's try another one. Let's try f of x is equal to sine pi halves x. And we're going to go over the same interval, -pi to pi, or -1 to 1. So where we're heading now is, it's going to go like this, right? So we see that at the points 1 and -1 and 3 and -3, there are these discontinuities. So here we have it's continuous and it's smooth. There are no discontinuities in the derivative or in the function itself anywhere for f of x is equal to pi x, but for pi halves x, the periodic extension has discontinuities in it. Okay. All right, now let's try another example. F of x is equal to we'll try cosine pi halves x. Okay, so let's look at this example. Draw another here. Put our 0 value. So at 0, cosine is 1. But when we go out to positive 1, we're going down to 0 there. We go down like that to negative 1 and 1. And then what happens is that we do another one. So this is sort of like hopping. Like that. Okay. Same thing back that way. So here we have, this is continuous, right? So the periodic extension, f tilde, is continuous at all these points, but not continuous in f prime, because you see those are sharp points. There's an abrupt change in slope. We go from a negative slope to a positive slope, a negative slope to a positive slope at a jump. So the derivative has a discontinuity in it. So these are just important examples that are kind of come up later. We want to just get these definitions down and show you some examples of how the periodic extension can create problems at the boundaries that may not even exist in the actual function, because over the interval negative 1 to 1, f of x on its own is smooth, and it's continuous and smooth. But when we look at the periodic extension, we all of a sudden get some difficulties in these functions. We can see that there's discontinuities. All right, so with that said, so now let's state the theorem of convergence. So we're not going to prove this theorem, but we're going to state that that here's the statement of the theorem. If f is piecewise continuous, or sorry, piecewise smooth, then the Fourier series, we'll call it f hat, and this is with n going to infinity. So in this case, f hat is equal to a0 plus the sum n equals 1 to infinity of an cosine n pi over Lx plus bn sine n pi over Lx. Then this function f hat has the property that f minus f hat, the distance function, is equal to 0, and f is equal to f hat wherever f tilde, the periodic extension, actually, sorry, I should say that, and the periodic extension is equal to f hat wherever f, the periodic extension, is continuous, and if x equals a has a discontinuous point in f tilde, all right? So we're looking at a point like this where we have a discontinuity, so that's x equals a. What we define here is we define this point what we'll call fa plus, and here we'll call that f of a minus, and that's equal to the limit x goes to a from the positive side of f of x. I should put this as the periodic extension, and that's equal to the limit x goes to a from the negative side of f of x tilde. Then, so at these points, our Fourier series, the value at a is equal to the average value of f a plus and FA minus. So in this case, what we mean is 1/2 FA plus FA minus. Okay, so what does that look like? So let's draw a picture of that. So what we're saying is, and I'll draw it a little bit bigger here. So if here is a periodic extension, there's our function from negative L to L, and that's going to go like this. Okay, so we see we have a discontinuity here, a discontinuity here. So this is f tilde. So that means that the function f hat, the Fourier series, will converge at every point we have continuity. F hat will be the same. But at the points where there's discontinuities in f tilde, f hat will be in between the two. Same thing here. There will be f hat, will be the point in between the two limits, which will be right there, in between the two limits. So this is an interesting form of convergence. So remember that we've never made the statement that f is equal to f hat, because that's not necessarily true. The same thing is true for the periodic extension. It's only true on a restricted set of cases. So something about our algorithm for generating our Fourier series, i.e. this thing right here, it generates a good approximation to f, but at points where there are discontinuities, we get different values. So they're not necessarily equal all the time. At these discontinuous points, the Fourier series arrives at a different value than the function itself. So there is the statement of the theorem, and that's how Fourier series works. So yes, we can state now that at least with our distance function, as n goes to infinity, we do get a better and better and better approximation. So that looks nice. All right, thank you very much.